All right, since we've talked about oxidation of alcohols to carbonyl compounds, we need to switch it in the reverse way and do reduction of carbonyl compounds back to alcohols. So for this one, we'll be starting off with a double bond and turning it into the single bond. So what we're doing here is adding hydrogens back into the system. So for instance, I want you to think about it like this. You're going to have two different styles, one that's weak and one that's strong. And of course, I'm going to do a problem for you so we can solidify these concepts ASAP. So when we have an aldehyde and so instead for oxidation, I had an O in the middle for oxidation. Now I have a hydrogen denoting each one of these. So for this one, for aldehydes and ketones, they can use the exact same one. They are limited to the weaker reagent. So we prefer to only use NaBH4 here, which reduces the system. Now that H plus again can be H2O or H3O plus or H plus. So what happens here is we get to break the double bond itself and add a hydrogen not only to the carbon, but to the oxygen as well. So in this case, when I break it apart, I want you to break it apart in this method. So that way, I'm just doing it on purpose so you can see it a little bit simpler. I kept the backbones of the original structure, but I'm saying you need to put a hydrogen where the carbon is and a hydrogen on the oxygen group. That's what creates an alcohol. An aldehyde can reduce to a primary alcohol, which before we learned oxidation, if I have a primary alcohol and I use PCC going this way, I can turn it into an aldehyde. I also want you to understand that NaBH4 is not the only thing that can work on aldehydes. We can use the Li, so I'm denoting that by putting it in pink. We can use the strong one, the Li, here as well. But when we're using the NaBH4, later you'll see that it cannot be used on carboxylic acids and esters. So the Li can work on everything, but the NaBH4, the sodium tetraboron, is only going to work on the aldehydes and ketones only. So again, the NaBH4 works on both. So if I start with the backbones of my ketone and I add the hydrogen to both carbon and oxygen, great, you make a secondary alcohol. You don't have to show the hydrogen that's connected to the carbon, so you don't have to worry about that one. And like I said, remember, that can work as well for the Li, LH4, and H+. Now, the Li definitely works on these because it's strong enough, but I cannot at all use the NaBH4 down here. So when I do the Li for the carboxylic acid, this one is a little bit, if we have to go through the mechanism, which we don't for in this case, the easiest way to remember it is lose the carbonyl and keep your OH. The hydrogens that you'll be adding will be replacing this oxygen, so they get added right here, giving you another primary alcohol. Esters are special in all cases, starting now all the way through the end of your Orgo 2 journey. Esters are special. I think about it like this. There was a woman named Esther in the Bible. Sorry for those who are not biblical or practice Christianity. When it comes to this particular point right here, I'm bringing this up because I know that in the Bible, it states that Esther's got double for her portion or suffering in a sense. So that helps me remember that I'll always get two answers for Esther's. Now that's my particular way of remembering it, but I mean, hey, if you don't want to use that, that's perfectly fine. Now for the esters, it's a little stronger. So what happens is same idea with the backbone, except for where it breaks, immediately when it breaks apart, you'll have two pieces. It's an automatic thing every time with esters. You're gonna put a hydrogen on each side as far as, so in this case, all 4 hydrogens will be used on esters, so you'll see them. You'll have the hydrogen on the oxygen, the normal one that you would put here, but then also for the break itself also counts as another hydrogen. So you'll get a primary alcohol on this side, and this side is going to just depend on what the picture looks like. It can be primary, it could be secondary, it could be tertiary, and in this case it happens to be secondary. Now, even though that was a lot, I still want to do a problem to help solidify it. So remember, NaBH4 only works with aldehydes and ketones, and Li works on everything. So when we see a problem like this, what you have to notice is, of course, I'm doing the problem in 2 different aspects, one with weak and one with strong. Well, this is your opportunity, and hopefully you've already done so since I mentioned it earlier, is that you need to review your functional groups, guys. So first I would start off and label every functional group you have in the picture, and then you just put the rules together with what you see. Now you see this one, they don't have to draw the hydrogen in for you to let you know it's an aldehyde. So please remember that, just in case you are moving really quickly and you just happen not to see it. So now let's talk about what our answers would be. If I have NaBH4, what functional groups should it work on? Correct. Aldehydes and ketones. So I'm expecting the ketone to turn into a secondary alcohol, and I'm expecting the aldehyde to turn into a primary alcohol. All I did was lose the double bond and make it an OH. Now for the rest of the groups, they stay in their format because the NaBH4 is not strong enough to actually break the carboxylic acid and ester. Now, in this case, it's gonna be strong enough for the carboxylic acid and ester, but that doesn't mean that you leave your ketone and aldehyde the same way. Here, everything changes. So the carboxylic acid, we just lose the carbonyl and we would be done there. The ketone becomes an alcohol, so it's the exact same from what we just did here. And then we remember that esters give us 2 pieces. Ah, there I go again, making errors. The ester, the carbonyl side, immediately gives us an alcohol. We break it apart right between the CO bond, so that's an ether bond. And then now this becomes that. And sometimes on the exam, instructors don't tend to show this piece because they automatically assume like it's a byproduct. No one really cares about that. So just in case you don't see it, it's still there, but know that esters will always break up into 2. So really use your oxidation and reduction charts together when studying. It would really help you out.